All right, let's dive into a really critical and often overlooked problem in statistical modeling, endogeneity. But more importantly, we're going to look at a seriously powerful and frankly pretty elegant way to solve it, called the Gaussian Copula approach.
So let me ask you something. Have you ever run a model and all the numbers look good, the results are significant, you feel like you're on the right track, but there's just this little nagging feeling, like, could something be off? Could there be some hidden flaw that's biasing your results, even when everything on the surface looks totally fine? Well, the answer is, very often, yes. And that hidden problem, it has a name: endogeneity. It's honestly one of the most serious issues you can run into with this kind of modeling, because if you don't find it and fix it, it can completely warp your results, and you might end up drawing all the wrong conclusions from your hard work. So, what exactly is this lurking problem? I mean, what are we really talking about? Because to fix it, we first have to get a really good handle on what it is. Okay, so here's the technical definition. Endogeneity happens when one of your predictor variables is correlated with the model's error term. Now remember, that error term basically represents everything your model doesn't explain. So if your variable is tangled up with that, it means some hidden factor is contaminating your results. And a lot of the time, that factor is a key variable that you just forgot to include in the model. Let's make this super concrete with a classic example. Imagine you're building a model to see if more education leads to a higher income. It's a simple, logical relationship, right? Education predicts income. Seems to make perfect sense. But hold on a second. What about a variable we might have left out? Something like a person's underlying intelligence. Think about it. Intelligence probably influences how much education someone gets, and it probably influences their income potential, totally separate from their degree. This omitted variable creates this kind of backdoor connection, and that's what causes the endogeneity. It biases the very effect we were trying to measure. For years, the main way to fix this was super complex and honestly often totally impractical. But today, we've got a much, much better tool in our toolkit, a brilliant, instrument-free solution. And this solution is the Gaussian Copula approach. Yeah, it sounds a little intimidating, but it's really just an advanced statistical technique that's designed to both detect and correct for endogeneity. And, the most important part, it does all this without needing to use what are called instrumental variables. And trust me, being instrument-free is a huge deal. The traditional method forced you to go on this wild goose chase, trying to find a valid instrumental variable. It had to be an external factor that was related to your predictor, but not to your outcome. Finding one that actually works is incredibly hard. The Gaussian Copula approach, on the other hand, is a total game changer because it just bypasses that whole search, and it cleverly models the hidden relationship directly to get the bias under control. Okay, so this sounds amazing, right? But when can you actually use it? It's a powerful tool for sure, but it's not a magic wand. There are some very specific conditions that have to be met. And here it is, the single most important rule. The Gaussian Copula method will only work if your data is non-normally distributed. This is non-negotiable. The whole reason it works is because it cleverly uses the unique shape, the skewness and kurtosis of that non-normal distribution to identify and model the hidden bias. If you have perfectly normal bell curve data, there's just no unique shape for the model to leverage. So how do you check for this? It's actually really straightforward. You can run standard statistical tests like the Shapiro-Wilk or the Kolmogorov-Smirnov test. The rule is simple. If the p-value from that test is less than 0.05, that means your data is non-normal, and you've got a green light to use the Copula method. So the decision process is pretty simple. First, you ask yourself, do I have a valid instrumental variable? If you do, great, you can use the traditional method. But let's be honest, most of the time, the answer is going to be no. So you move on to step 2. Is my data non-normal? If the answer is yes, you're in business. Go ahead and apply the Gaussian Copula approach. If your data is normal, well, then this method just isn't the right fit. Now, here's a quick practical tip for when you have more complex models. What if you suspect that more than one of your variables has this endogeneity problem? No problem at all. The process is exactly the same. You just have to apply it individually. You'll create a separate, unique copula term for each and every potentially endogenous variable in your model. Okay, so you've done your homework, you've checked your data, you've run the model with the copula term included. Now for the moment of truth. What do the results actually tell you? Interpreting this all comes down to the significance of that copula term you added. If the path coefficient for the copula term is statistically significant, that's like a big red flag. It's telling you, yep, endogeneity was present and your original results were biased. But the good news is, by including the term, you've now controlled for that bias. Now, if the copula term is not significant, that's also great news. It basically means your model was robust and probably free from endogeneity all along.
So we've seen how powerful this is, but like any advanced method, it is absolutely crucial to understand not just what it can do, but also where its limits are. You've got to keep 3 key limitations in mind. First, this method really works best when you have a large sample size. Second, and I can't stress this enough, it absolutely positively requires non-normal data. And third, it can be a little less effective when you're working with single-item constructs, simply because multi-item scales give the model more stable information to work with. So here's the real takeaway. The Gaussian Copula approach isn't just some fancy statistical trick. It's a robust, powerful tool that, when you use it in the right circumstances, can dramatically improve the accuracy and the trustworthiness of your research findings. And that really brings us to our final thought. Learning to identify and correct for a hidden problem like endogeneity, it just makes us better, more critical researchers. It encourages us to think more deeply about our work. So, now that you know how to look for this, the question to ask yourself is, what other hidden assumptions might be lurking in your own models?